Welcome to this explainer. Today, we're taking on a genuinely fascinating challenge. We're going to demystify the black box of random forest regression. I'm so excited to guide you through this, because we aren't just skimming the surface here. We're going to trace this incredibly powerful machine learning architecture all the way from its pure underlying mathematical theory right down to a real-world application in material science. Whether you're a seasoned data scientist or just kind of dipping your toes into predictive modeling, we've got you covered. Okay, so here's our blueprint for today. We've got 6 sections. First, the core intuition. Second, architecting the ensemble. Third, the micromechanics of node splitting. Fourth, a real-world application predicting yield strength. Fifth, tune in the architecture controls. And finally, decoding feature importance. Let's jump right in. Section 1, the core intuition. To really grasp the sheer power of a forest, we first need to talk about the inherent vulnerability of just a single tree. Let's establish the fundamental paradigm here. Think of a simple decision tree like a highly overconfident expert. It's incredibly sensitive to noise and honestly super prone to overfitting. It essentially just memorizes the training data instead of learning the actual underlying patterns. But a random forest? That's an ensemble. It acts as a vast committee of independent experts. By working together, they structurally neutralize each other's individual errors. This concept of ensemble averaging is brilliant. Imagine one isolated tree predicts a value of 4.8, and another gets a bit sidetracked by noise and spits out 5.2. Well, the random forest doesn't panic. By aggregating these individual, slightly flawed predictions, the system achieves remarkable stability. Those individual biases literally just cancel each other out, leaving us with a highly accurate, stable, average prediction of exactly 5.0. Section 2, architecting the ensemble. Now, that all makes perfect sense in theory, right? But it immediately raises a huge question. How do we mathematically guarantee our committee of experts doesn't just make the exact same mistakes? The algorithm solves this beautifully. It uses 2 crucial mechanical steps to actively force structural diversity across all the trees in the forest. These 2 pillars are bootstrapping and feature randomization. Let's look at step 1. Bootstrapping, which is also known as bagging, is how we get data diversity. The algorithm samples the original training data set with replacement. That means individual data points can pop up multiple times in one tree's training set, but be completely absent from another's. It's generating parallel data sets so no 2 trees are ever looking at the exact same picture. This guarantees structural independence so they don't learn identical error patterns. Moving on to step 2, feature randomization. This is where it gets incredibly clever. At every single node split, the algorithm evaluates only a random subset of the total features. Why is that a game changer? Well, it actively stops a single, loud, dominant variable from driving every single tree's decisions. It literally forces the forest to dig deep and explore the nuanced, hidden relationships within weaker, secondary variables that maximizes the variance reduction power of the entire ensemble. Section 3, micromechanics of node splits. So the really crucial thing to understand now is exactly how these individual node splits are decided mathematically once we've randomized our data and features. Let's zoom in. Taking a microscopic look here, a single node is basically a relentless optimizer. It continuously iterates through variable thresholds, hunting for the exact mathematical split that minimizes the mean squared error, or MSE. By minimizing this variance between the actual true value and the mean predicted value at the node, it effectively slices that messy data into much cleaner, homogeneous child nodes. Zooming all the way back out to the whole forest, the big takeaway is a very elegant equation. The final predicted value, y hat, is simply the mathematical average of the predictions from all those independent decision trees. By doing this, the random forest keeps the low bias capability of deep, complex decision trees while systematically crushing their high variance over fitting vulnerabilities. It is truly the best of both worlds. To put this into perspective, just compare the random forest to simple linear models. In the physical sciences, properties rely on simultaneous, multidimensional interactions, like temperature interacting with cooling rates. Linear models completely fail at capturing this complex nonlinearity unless you sit there and manually program in every single interaction. But random forests, they naturally map out these automatic interactions and multidimensional landscapes without needing any manual input from us at all. Section 4, application, predicting yield strength. All right, let's pivot from computer science theory over to applied material science. We're going to deploy this exact random forest architecture into the real world to solve a genuinely tough engineering problem. Our mission here is to predict the mechanical yield strength of an alloy, which is a highly nonlinear physical property. We're working with a messy, multivariable data set. We've got varying percentages of carbon and manganese, different microstructural grain sizes, and varying processing temperatures. To tackle this, we'll use Python's scikit-learn library. We initialize a random forest regressor and strategically split up our data. We're feeding 80% of our known data in to train an ensemble of 200 independent trees, and we're holding back 20% to test it later. We also set a max depth of 5, just to keep the complexity in check. After fitting the model to the training data, we ask it to predict the yield strength on that unseen 20% test data. And wow, the resulting R-squared score is an absolutely staggering 0.9879. Let's break down what that number actually means in reality. When evaluating the predictions, we see an incredibly tight clustering right along the ideal trend line. An R-squared score of nearly 0.99 mathematically confirms that our ensemble successfully bypassed the noise of a limited dataset and isolated the true underlying physics of the material. It didn't just memorize the data, it actually learned the physics. And what's truly fascinating is how the model actually achieved this accuracy. It didn't do it by drawing simple, straight, best-fit lines. Instead, the model dynamically contoured its predictions to perfectly match the distinct, exponential, and interactive physical responses of each individual feature, like carbon or grain size. It mapped the messy, nonlinear reality. Section 5. Tuning the architecture controls. Okay, before we declare total victory here, we need to understand the levers we pulled to control the algorithm's complexity. Because, you don't just hit run without tuning the engine first. By adjusting hyperparameters, we keep tight control over the architecture. For instance, setting n_estimators to 200 gives us a high total number of trees for stability. We control max depth to act as a ceiling on complexity so the trees don't grow too deep and overfit. And we use min_samples_split as a smoothing mechanism to prevent the model from learning ultra-specific noise at the very bottom of the trees. Fine-tuning these dials is exactly what gave us that 0.98 accuracy. Section 6. Decoding feature importance. Finally, let's open up the proverbial black box. A really common critique of machine learning is that it's uninterpretable, but random forests actually let us peek inside to see exactly which features mathematically drove those incredibly accurate predictions. By extracting the mathematical weights for how much each variable reduced variance across the entire forest, we get a super clear hierarchy. Carbon is the primary driver of yield strength here, which makes perfect metallurgical sense. But look what comes in a close second: grain size. This perfectly and entirely independently aligns with the established physical laws of the Hall-Petch relationship. The algorithm didn't just find some random correlation, it validated established physics without ever being programmed with the laws of physics. That is mind-blowing. All these mechanisms combine to give us 3 major architectural takeaways. First, we achieve structural robustness through the data diversity of bootstrapping and feature randomization. Second, we got variance optimization through that mathematically ruthless MSC node splitting. And third, through ensemble averaging, we generated high-fidelity aggregate insights that finally unlocked the black box of multivariable interactions. Because random forests transform mere predictive accuracy into true, verifiable scientific interpretability, it leaves us with a pretty profound realization. We just saw how this architecture learned the Hall-Petch relationship entirely on its own from a small, messy dataset. So I gotta leave you with this question. If an algorithm can independently map out the complex physics of alloys today, what entirely new scientific laws is it going to discover tomorrow? Thanks so much for exploring this with me.